Hey guys, we're going to go over quantifying heat right now, and so that's an important thing for us to be able to do. We're going to want to be able to get at this number Q. It's a really important one, how much heat is going into or coming out of something. So that depends on three different values: the mass of something, which we usually abbreviate as M, a quantity known as specific heat, and we'll get to what that means in a minute, but that usually gets the symbol C, and then the temperature change, and that usually gets the symbol delta T, change in temperature. And the way we do changes in temperature is T final minus T initial. So if something is gaining or losing heat, its temperature is definitely changing. So the temperature it started at, its initial temperature, and the temperature it's ending at, its final. The difference between those two, in the order of final minus initial, is what delta T actually is. So the equation that we can write for something like that is Q is equal to MC delta T. Almost looks a little like MCAT. So M times C times TF minus TI is another way to look at it. So that's a good way to go. And if we're doing this in terms of units, this mass has units of grams, and this temperature has units of degrees Celsius. Q must have units of joules, so this C, in order to make these units work out, must have units, I'll put it here in parentheses, of joules per gram degrees Celsius. And this right here, which is what's usually known as the specific heat of any given substance, it's a number that is unique to every single substance that is out there. Now, these are not numbers you need to memorize, but I hope you can appreciate what the numbers actually mean. So for lead, the specific heat capacity is 0.128, and it's the same for gold, 0.128. Aluminum's got a slightly higher one, 0.903. Ethanol, one of my favorites, is 2.42, and water is 4.184. Water's got a very high specific heat. What does it mean when a specific heat is very high? So if I want to heat 1 gram of a substance by 1 degree Celsius, for water it would cost 4.184 joules. That's for water. For lead it would cost 0.128 joules. So a high specific heat means it takes a lot of energy for me to heat 1 gram of one substance 1 degree Celsius. Basically, it takes a long time to heat water, and once water is hot, it takes a long time for it to lose heat. Lead, on the other hand, takes very little energy to heat. If I was to give this some energy, it would end up, heating up pretty quickly. And once it got hot, it would probably end up cooling down pretty quickly. So this specific heat basically tells us how easy or how hard it is for us to heat something. Now there's some math that we can do for this, and I know you were excited about the math, so here it is. We'll work through two different examples here on the same page. First example is how much heat in joules is absorbed by a 3.10 gram penny made of copper when it goes from -8 degrees to 37 degrees. So we've got most of what we need here. We have a mass and we have a temperature range. We don't have a specific heat, but that's not what we're being asked to calculate. We're being asked to calculate the heat in joules. So we should be able to look up the specific heat of copper, and we can. It's 0.385. There's a table in your book, or a lot of times books will just end up giving you this as part of the problem. So don't worry if you don't know that number. If you know the substance, you can always look it up. So how much heat in joules? So this is our equation, M times C times T final minus T initial. So we're just plugging in the things that we know here. 3.10 grams. 0.385 joules per gram degree Celsius, and 37.0 minus -8.0. All right, there are no variables in here, so whatever comes out should be my answer in units of joules, and when I go through and do that, I get 53.7 joules. Okay, so it doesn't take a whole heck of a lot of energy for me to heat a penny from very cold to, body temperature. Let's look at the second example where we have to find something else. A 55 gram aluminum block is heated, with a temperature of 27.5 degrees, absorbs 725 joules of heat. What is the final temperature? So here I'm given a mass I'm given a initial temperature and a heat. I need to find the final temp. So let's figure out how we do that. Again, here's our equation. Q equals m times C times T final minus T initial. And my mass here is 55.0 grams. My C, again, it's not given in the problem. I'd look it up from a table, is 0.903. So 0.903 joules per gram degree Celsius. And then I need to find my final temperature. So that's my variable, TF, minus my initial temperature of 27.5. And all of this should equal 725 joules. Okay, so if I go through and do my math, 725 joules, I'm going to show all my steps just to be explicit. So 725 joules, combining these two terms, gives me 49.665 TF minus 27.5. If I divide both sides by this 49 number, I get 14.597 equals TF minus 27.5, and then I just have to add 27.5 to both sides so that I get TF by itself. And when I do that, 42.1 degrees Celsius is my result. Okay, so the math here is really not all that hard. All we have to be able to do is realize what we're given and work within this formula. There's only a few things in it, and we should be able to get to where we need to be. But the much more interesting problem, the one we're kind of working up to, is quantifying heat in terms of a thermal transfer. So let's imagine that we've got some water inside this beaker here, and we drop in a hot block. And that hot block is going to end up exchanging heat with the water that it's in. So this hot block is going to end up losing some energy, and this water is going to end up gaining some energy. And because of the first law of thermodynamics, the sum of those two things is 0. There's no net gain or net loss of energy anywhere in the universe. So if I just sort of rearrange this a little bit, the heat gained is equal to the negative of the heat lost. Okay, so if I wrote equations for these things here, so m times c times tf minus ti, that's my gained here, so this is my q gained. And negative, put this in brackets, m times c times tf minus ti. And this is my q lost. Okay, so that's what this expression here is. I've just sort of put it in terms of the equations, and I'm splaying them all out. So how can I go through and do this? Well, I'm going to leave this side the same because nothing here changes, but I'm going to distribute this negative sign, so this becomes negative m times negative c, put these in parentheses so I don't lose them, times, let's see here, in brackets, negative tf minus ti. And now I can start multiplying these things together, so negative m times negative c is the same as m times c. Negative times negative is a positive. And then this here becomes negative tf plus ti. Negative times positive is a negative. Negative times negative is a positive. And this rearranges itself to m times c ti minus tf. Okay, so putting that negative sign here, all it really does is switch ti and tf. So m times c times tf minus ti for whatever is gaining energy. And this is what the expression looks like for whatever has lost energy. That's going to become important as we do the big problem that we're working up to. And that is this. I've got a 32.5 gram cube of aluminum. Their specific heat is given. And it initially has a temperature of 45.8 degrees Celsius. It gets submerged into 150 grams of water at that specific heat, and its initial temperature is 16 degrees Celsius. What's the final temp of both the aluminum and the water? So when this is done, these are going to have the same final temperature. Okay, when all is said and done, one is not going to be hotter than the other. That's the point. So I'm going to have a Q for the water, and I'm going to have a Q for the aluminum. Okay, and I'm just going to plug in the things that I know. So for the water side, it's 150.0 grams times 4.184 joules per gram degree Celsius times whatever the final temperature is, minus 16. And then on my aluminum side, 32.5 grams of aluminum is what I have, and 0.903 joules per gram degree Celsius. And it's going to be initial minus final on this side, so it'll be 45.8 minus my final temperature. Okay, notice I've got the same variable on both sides. All I got to do is the math to isolate it. So if you like watching people show their work, then this is for you. So when I combine these terms, it's 627.6 TF minus 16. When I combine these two terms, it's 29.35, 45.8 minus TF. Okay? And when I distribute these terms here, so 627.6 times TF minus this number times that number, which is 10041.6. Same thing on this side, this number times this number, 1344.12 minus 29.35 times TF. Okay, my goal is to get TFs on the same side of the equation. So to do that, I'm going to end up adding this to both sides. So when I add this number to this number, I get 656.95 TF. And when I add this number to this number, I get 11385.72. And all I have to do is divide both sides by 656 to get TF by itself. And when I do, I get 17.3 degrees Celsius. So that is my result. You may realize that the water, originally our water was at 16 degrees Celsius. It heated up to that. And our aluminum was at 45 degrees Celsius, 45.8 actually, and it cooled down to that. This lost as much energy as this gained, but it takes a lot more energy to heat water than it does for aluminum. And that is a consequence of having a very high specific heat. Okay? So that's an important thing for us to sort of keep in mind as we get these numbers. We do all this math, we get a number. Does it make sense? All right. So the last thing here is quantifying work. Now this is nothing we're really going to do a lot of work with, but the thing I really want you to realize here is that the equation for work is equal to force cross distance. That is a force applied over a distance. So if something hasn't moved, work has not been done. If we do a little bit of math on this, then we can rewrite this equation as work is equal to the negative of the external pressure times the change in volume. That becomes important in other parts of a chemistry class. We're not going to quantify much with this, but here's the basic idea. Let's imagine I've got like a gas cylinder here, and I've got some gas particles, and there's a piston here on top. And if that piston is pushed down, the gas particles here are really close together, and that creates a high energy situation. So work has been done on this system. So it has a positive value. The smaller v right here means that our volume has decreased, so work has been done on it. Conversely, if these particles now have more space to spread out, okay, that means that this system did work on its surroundings, so it lost energy. So it ends up having a negative value. So it expands. We have a larger volume. Okay, so quantifying heat and work, those are the big two topics here, but really focus on quantifying heat. All right, we'll see you in the next video.